the default R graphical user interface. But as a reminder, this is all the same if you're using RStudio. This version of the interface has less stuff, but we're basically focused on commands that we're going to issue to the console, which in RStudio appears in the lower left. And I'm going to get those commands from this code file, which is not in RStudio in the upper left, but I'm going to move it over to the right so that there's more room to see the output and the code at the same time. Is this big enough to read? Okay. Some nods. Okay, good. So the idea today is to quickly review some of the things we've talked about so far, and then show you, start to finish, some very simple procedure of reading in a data file from the computer, and then making some cool, sort of cool plots from it. I know that I'm real nerdy, and so, calling plots cool is, I want to convince you that you can, if you have data that you want to explore, you can do it using R, and you can make some colorful graphs that will be useful for what you're trying to accomplish. And even if you don't know how to do everything yet, you can still try to do stuff like that. I'm actually going to move the code over so that Zoom can be here on the right-hand side. And please jump in with questions whenever you want. I will remind you of this in a little bit when we get to this point, but I have opened this code file in a folder on my computer that contains the comma_separated.csv file of data that I emailed out last week in a zip file, so that we can use it as an example. So that data file is in the same folder as the code. If you are following along on your computer and you don't have that data file, you can retrieve it from my personal website, sarahemilyburke.com. And I clicked on the statistics page, and there's this R workshop stuff at the top. This link takes you to some videos. This one takes you to a PDF summary of a workshop that I did. And then this one here, our workshop example data and syntax, if you click on this, it will download that exact same zip file that I emailed out to everyone last week. So you can get another copy of it, and it contains the data example that we're using today. Okay, so here's the quick review. These are things that we talked about in the last couple of weeks. When you're using R, you will want to be able to assign values to variables. So for example, x equals 3 changes the value of x to 3. X didn't exist before, but now it does, and it's just the number 3. But it doesn't have to be a number. It can be a string like ASTF. And then when we ask R what x is, it will tell us ASTF. The equal sign is one way to accomplish this. That's how it's done in most programming languages. You can also use this arrow constructed from the less than sign and then the negative sign. As long as they're right next to each other, it won't interpret it as less than and negative. It will interpret it as the assignment operator, the same as the equal sign was doing up above. So that changes the value of x to 3. And we've learned about vectors. Those are ordered sets of values. So if I use this C function for concatenate, and now x is 2, 4, 6 in that order instead of just a single value. And that becomes extremely useful when we're doing statistics, because almost always we have basically data that we want to think of as variables with observations from multiple participants in them. So this could be 3 students' scores on some kind of a test. The first one got a 2, the second one got a 4, and the third one got a 6, for example. And then I can do statistics on that. I mean, a sample size of 3 is not really enough to do very much of interest, but this generalizes to longer vectors. And when we have a vector, we can use it in various functions. Functions are objects in R that have a name, just like other kinds of variables, and then they have parentheses after, and you provide arguments separated by commas in the parentheses. So x is 2, 4, 6. If I ask R what is the length of x by using the length function, then I get 3. There are 3 elements in x. mean of x is 4. That is what you should get if you calculate this numeric mean in your head. You can do 2 plus 4 plus 6 and divide it all by 3 if you want. It will come out to 4. And I can have more complex functions that have multiple arguments, again, separated by commas. So rep repeats something. If I do rep where the argument is x, the first argument is x, and the second argument is each equals 2, then I'm telling R to repeat the vector x, where it's repeating each element twice. So x is 2, 4, 6. Rep x each equals 2 gives me 2, 2, 4, 4, 6, 6. These are just examples of functions. And then we have data frames, which are arrangements of many vectors, which typically is the structure our data takes when we do an experiment. And we tend to think of those vectors as columns in the data frame. So MT cars is an example data frame built into R for teaching like we're doing now. And you can see that the first column is called MPG, meaning the miles per gallon that each of these cars got on some test. And it has many values in it, but it's just MPG is just a vector, just like X that we were working with a second ago. And we can retrieve specific vectors from a data frame using the $sign. So MT cars $HP gives me the horsepower vector extracted from this big table. That's what the data frame is. So that's all recap. And last time we did an example of reading some data files into R. And the most useful, the most generally applicable one is when you have a comma-separated values file. If you have a CSV file on your computer and you double-click it, if you're running any modern version of Mac OS or Windows, it will probably try to open it in a spreadsheet program by default, such as LibreOffice Calc or Excel if you have the Microsoft Office suite installed. It's a perfectly good way to look at the data. But of course, we want to be able to get those kinds of files into R too. And the read.csv function is designed for just that. So this comma separated.csv file is the name of a file in the folder that I'm working in already on my computer. And that you can have this data set too if you go download it from my website or look at the email that I sent last week. And all I need to do is plug that into the read.csv function, and it will read the data file. And then I'm going to use the assignment operator to give it a name so that I can use it in R. And for now, I'm just going to call it dat. So now that I've done this line of code, dat is a thing that exists just like MT cars in R. It has a name, and it contains a particular R object. Just like previously X contained the number 3, now dat contains this whole table, which is a data frame with 4 vectors in it called gender, age, race, and score. It's not real data. I don't even know what the score is supposed to be. It's just an example of the kind of data set you might have if you do a small experiment. And I think last time we talked briefly about doing a t-test on data like that. So maybe we want to test the gender difference in the scores in this data file, this data set. And I can do that by doing t.test. That's a function, so it has parentheses. And I'm going to provide 3 arguments this time. This is the most complex function we've looked at so far in today's examples. The first argument is what variables I want to test. Score is the response variable or the dependent variable. The tilde is the symbol that separates the dependent variable or response variable from all of the predictor variables or independent variables. And then gender is the one predictor variable. This is my way of telling R, I want to compare the average scores between the 2 gender categories that exist in this data set. I can see the data set over here. It's a very small one, so I can see it all at once. I did that on purpose so I could show it on the screen. And I can see that there are just 2 unique values in this data set for this column. So I can do a t-test. That's the first argument. I haven't specified dat $sign score, though. And remember, these variables are inside of this data frame. So I could do dat $age to get the age vector out of the data frame. That would be totally fine. But when you're doing a t-test, you can also avoid having to do that by just providing another argument. And that argument is called data. And the value I'm assigning to it is dat, which is this thing that I read in from my computer a few seconds ago. And what this tells R is that all the variables that I'm using in my formula over here come from this data set. And then I don't have to do dat $score and dat $gender. And the third argument is this var.equal thing that we looked at last time, which tells R that I want to go ahead and assume that the variances are equal. If you took the Intro to Stats class here at SU in the Psych department, then you would have learned that a t-test, the normal way of doing a t-test, we assume that the variances of the two groups are equal. That's not always a good assumption, and there are ways to fix it, very easy ways to fix it. But for now, let's go ahead and keep with that standard assumption. And now I will run the t-test with this single line of code, one function, 3 arguments, and I get some results. The mean in the F group is 5.7, the M group is 6.0. So the men in this sample had a slightly higher score on whatever this test is, but the p-value is 0.83, which means it's definitely not statistically significant. We're looking for low p-values to call something statistically significant. By convention, lower than 0.05. And this is nowhere near that threshold. And so basically, we cannot rule out the possibility that men and women are scoring equally on average on whatever this test is that I have implemented. So that was all review. Any questions about any of that stuff? Cool. So now I want to show you some new stuff. And the first thing I want to show you is a simple linear regression. Linear regression is just a way of calculating an association between two numeric variables. And the function for it in R is LM, which works very much like this t.test function we looked at a second ago. LM just stands for linear model. And here I'm only providing 2 arguments, the formula and the source of the data. So there's nothing fancy going on here. This one looks just like this one, except score is my dependent variable or response variable. And now I want to use age instead of gender as my predictor variable. And I'm going to get both of those variables from this data frame called dat, which we can see again right here. And it has 4 variables in it, and one of them is indeed called age. So it's totally fine for me to do score tilde age with that data set. But this time, instead of just running this statistical function on its own, I'm going to use the assignment operator to give the results of it a name, which I'm just calling score age regression. This is my own name. You could call this X, or you could call it turtles, or any of the other variable names that we've used before. But in this case, I chose this highly descriptive name for the sake of example, because it's a regression of score and age. So I get no output when I run this line of code because I just ran the regression model and stored the result with this name. So if I want to see some results of it, I might do things with this object. And with regression, it's typically useful to use the summary function to get information about the regression model. So now I'm going to run summary with this one argument, score age regression. And here I get a conventional regression table. And typically, the first thing that most people will look at is the slope of the predictor variable, which is age. And the slope is 0.19, 0.1855. And what that means is that participants who are 1 year older in this sample on average score 0.19 points higher on whatever this test is. The older participants are scoring higher. And this answers the question, how much higher? Each year of age is associated with about 0.19 points on whatever this score metric is. And this one has a p-value that is 0.002. So that is a low p-value, well below 0.05. So by convention, we would call this one statistically significant, that age is significantly correlated with score, and older participants are scoring higher. And that's all well and good to get those numbers, but often it helps to be able to visualize this kind of stuff. So for most of the rest of today, I'm going to focus on plotting because I think that is part of what makes it fun. So let's start by looking at a very simple scatter plot. The next function I want to show you is just called plot. This function has a very generic name, and that suits its very generic purpose. You can do all sorts of things with it. It will basically try to guess what kind of plot you want based on what argument you provide. But score is a numeric variable and age is a numeric variable, and I'm going to do this score tilde age thing, just like I did for the regression model up here, implying that score is the dependent variable and age is the predictor variable or independent variable. And they're both coming from this data set. And we'll see what R does with it. It gives me a scatter plot, which makes total sense for two numeric variables. And each of these little circles is one of the points. And you can see why there was a positive association between age and score. We've got a couple of outliers here in the upper left, but overall, there very clearly is a positive relationship between age and score. Older participants are scoring higher on average, and there's just two younger participants who scored quite high. If you're doing this in RStudio, this plot will show up in the lower right-hand corner of the screen, pretty small by default. But this is another reason why I like teaching using the base R GUI, because then I can show the plot nice and big over here. I'm just covering up the console with it because we don't need that for a second. We'll go back to it pretty soon. I want to show you one more function though. AB line is a function designed to draw lines on plots. So we've already got a plot. We can use AB line to add a line to it. And the only argument I'm providing is the score age regression model that I created earlier on. This score age regression thing, again, is my own name. That's not a technical R term. That's just a variable name I created for the sake of this example. And when you have a regression model, it is estimating the slope between two variables, the line of best fit. So it makes sense that you would be able to use that regression model to actually draw that line on a plot. You want to make sure you're drawing it on the right plot, a plot that has the same variables as the regression model is using. Otherwise, it won't actually match the points there. But in this case, I know that score age regression is based on score and age age are exactly the same variables that I plotted here. So this line fits those values. And this is a good general lesson about fitting regression lines too, because you can see that the line doesn't really pass. It's not like if you were to draw a line through where most of the points seem to be, you might have drawn it with a steeper slope. But these two outliers who have young age but high scores, they sort of pull up the bottom of the line because the average score down here is a little bit higher than where this cluster of points is. It's brought up by these two outliers. Otherwise, the relationship between age and score would be even stronger.